Okay, this video is for AP Calculus, and it's on the derivative units. We're talking about the chain rule today, which is one of the most important properties for derivatives. We use this all the time. And the chain rule says that if you are taking the derivative of a composition of functions, which means one function is inside of the other function, then we have to use this chain rule. So let's say that we have y equals e to the, and I'm going to change colors here to show something, x squared plus 3, then that means that we have a function x squared plus 3 that's plugged into another function, e to the x. Right, so this is called a composition of functions, and this red function here, we refer to that as the inside function, and this e to the raised to the something, e to the x function, is the outside function. So the chain rule says that the derivative of that structure is, if you want to take the derivative of a function g of x inside of a function f of x, first you take the derivative of the outside function and you leave the inside plugged in as is, but then you multiply by the derivative of that inside function. Right, so the reason it's called the chain rule is you always take the derivative of the outer function, but then you just add a link to the chain by multiplying by the derivative of whatever inside that. And as we'll see in some later examples, that you can have functions inside of functions inside of functions, and so you keep multiplying by another link in the chain until you finally have just x as the input. So this right here, let's say that we've got this is y, and so we're going to take the derivative, I'll mark that as y prime. We'll start by taking the derivative of the outside function, which is e to the x squared plus 3. But then because this was anything other than just the variable x, it's a function. And then we have to go ahead and take the derivative of that and multiply by that. Multiply another link in the chain, the derivative of what was inside. And that's it. That's the chain rule. So not difficult to understand conceptually, but sometimes tricky to implement. Okay, before we look at other examples, we can use this to develop a shortcut to find the derivative of logarithm. We don't have that on our list yet. How do you take the derivative of natural log or log base 3, something like that? So what you can do is you can start with the equation y equals natural log of x. Take e to both sides, raised to both sides. This will give you e to the y on the left side, and e and natural log cancel and give you x over here. And then if you take the derivative of the left side, that would be the derivative of e to the y, which means we would take the derivative of the outer function, right? But then we would have to multiply by this derivative of the inside. We don't know the function, but we can write that derivative as dy dx. Right, so you end up getting e to the y, dy dx equals the derivative of this x, which is 1. And if you divide both sides by e to the y, you get dy dx equals 1 over e to the y, but e to the y is simply x, so that means you can replace it with x. And that means that the derivative of the original y is 1 over x. And since the original y was natural log of x, that means the derivative of natural log is simply 1 over x, 1 over whatever is inside the log. So this is a new shortcut for us to add to the list that we need to memorize. Right? And if you have an arbitrary base, so let's say you're taking the derivative of some base other than e, so like say log base 3, something like that, and then that is going to be 1 over the inside, which is x, but then you have to divide also on the bottom by this natural log of that base, right, to change that base. All right, so that's 2 new shortcuts that we can add to our list of things to memorize. What we're going to do next here is look at some specific examples that get more complicated. The reason this is called the chain rule is you can have many functions nested inside each other. You always start with the outermost function and take the derivative, and then you multiply, you chain on the derivative of the inside, and you keep going until the function you're working with is simply x. I'll show you by changing colors here. So looking at this function, y equals natural log of sine of e to the x to the 5th, that means the most outer function here is the natural log. So I'm going to make that a blue. And that means that the derivative is going to be the derivative of the natural log, which we just found out is 1 over whatever is in the inside. And so what's inside there is this. Okay, so I simply copy that. It's 1 over that. The derivative of the outside is that. Okay, the next function, this sine of x, that's inside the other function, right, that means that we have to take the derivative of that. So the derivative of sine is cosine. So it's going to be cosine, and then whatever's inside of that, we just copy. Right? But now, what's inside that? What's inside that is this e to the x function. Right? So now I'm going to multiply by the derivative of that, which is an exact copy. Right? And at first I'm copying the inside of that. Okay? And then we're going to multiply by the derivative of the inside of that. So the derivative of the inside of that, well, the inside function here is x to the fifth. So that is a power function. And that means that derivative is 5 times this raised to the fourth power, and this is an x. Okay. Now, at this point, we don't have to go any further because the inside function right here is just x. Use a darker color. Right? And the derivative of that would simply be 1, and so the chain stops. So you stop when you get to the function that you're finding. The input to that is just x. So you could say that this function was x to the fifth, so the input to this function is simply x, and so we're not going to have to do any other change past that derivative. So it's a derivative of log 1 over the inside, times the derivative of sine, which is cosine, and then times the derivative of what's inside that, which is the e to the x, so that's a copy. The derivative of the inside of that is 5x to the fourth, and then the inside of that is x, so we stop. That's why this is called the chain rule. We can do this as many things as we want. Remember, these things are all multiplied together. All right, let's look at another example of that. So here, I'm going to rewrite this one more way here. So this is really the equivalent of sine of x cubed plus 7x, but then that cube applies to the whole sine. So it's like that's the outer function. So that means the derivative here is going to be first the derivative of this x cubed, which is 3 times whatever is inside of it. I'll change colors when I do that. So what's inside of that function is sine. I'm going to highlight something here. Inside of that is this x cubed plus 7x. And here's the end of the sine function, right? And then we're in the process of taking the derivative of this 3, so that it's 3 times that squared, so the derivative of the outside function. And then we're going to multiply by the derivative of the first thing that's inside that. So this function here, its outermost function is sine. So we're going to take the derivative of sine, which is the cosine, right? And inside that, we have this function, which is x cubed plus 7x. Close that cosine function. Then we have to take the derivative of this, right? So we're going to multiply by the derivative of that, which is 3x squared plus 7. And I don't have to go any further than that because what was inside that polynomial was simply an x. And so the derivative of x would be 1, so we stop. So that's how chain rule works. Okay, so that means you can extend any other shortcut. Like we just saw that if you take the derivative of sine of x, that's cosine. So the derivative of sine of any other thing is just the cosine of that thing, but then times the derivative of that thing. Right? So number 5 here, for example, that is y is sine. So that means that the derivative would be the cosine. And at first we just copy the inside. But then we have to multiply by that derivative. If it's anything other than x, even negative x, the derivative would be negative 1. But here, the derivative is 6x plus 1. That works with sine, right? It extends the sine derivative shortcut to the sine of anything now. And the power rule one, this is another example, number 4. The outermost function here is raising to the fifth, so that means we're going to say 5 times whatever's inside that, just copied, but to the fourth. So 5 that to the fourth times the derivative of the inside, which in this case is 3x squared plus 4. We don't have to go any further than that because the polynomial, its input is just the x. The derivative of that x would be a 1. These are multiplications here. All right. So just a few more examples here. These are actually more like the way you would see this asked in a multiple choice question on an AP exam. Let's say that we define u of x as f of g of x, v of x as g of f of x, and w of x as g of x. Find the derivative, or if it doesn't exist, explain why. So the first question here we're doing, number 6, you can try this on your own if you like. We're going to go ahead and take the derivative of u with a 1 plugged in. So I think first what we should do is take the derivative of just the generic ux. So if u of x is f of g of x, I don't know what the functions are, but I have some graphical representations here. That means that the derivative by the chain rule, u prime, would be the derivative of the outside function, which is x. I'm going to write that as f prime, and then leave the g of x plugged in without change, and then multiply by the derivative of the inside function g prime of x. So first I'm going to apply the chain rule to write out what the derivative of u prime would be at any x. And then I'll go ahead and plug in the x they want us to evaluate at, which is 1. That's f prime of g of 1, replacing the x with a 1, times g prime of 1. And then let's see, this g of 1, that's the y-coordinate of the g function at x is 1. So the g function is this red function here. The y-coordinate at 1 is 1, 2, 3. So that means this is a 3. So now I'm taking f prime of 3 times g prime of 1. These are both derivatives, which means they're the instantaneous rate of change of the function. So like the f function is this blue function. F prime means the slope, if you will, of that function at x is 3. So 1, 2, 3, that's here. The f function's slope in this region appears to go, let's see, we go down 1 for every 1, 2, 3, 4 that we go over. Down 1 over 4 is negative 1/4, right? So this would be negative 1/4 for that slope. And then the g prime, we have to go to the g function. Now we're evaluating this at x is 1. So at 1, the slope here is up 2 for every 1 that we go over. So that is a slope of positive 2. So you could leave it like that, or you can simplify this to negative 1. All right. Actually, so g prime of 1. Sorry, I think I used the wrong function. Let me go back. I was just looking at my cube. So this one is negative 1/4, but I used the wrong function. We have to use the red function. The red function is the g function. To evaluate that here, the slope here is down 1, 2, 3 for every 1 that goes over. So that's actually negative 1/3. And so that's positive 1/12. You can either leave it like that, or you can simplify. On the AP exam and on our exams, if you do simplify, then you have to simplify correctly over these points. All right, so here's another one that's similar. See if you could try this one. Pause the video, give it a shot, and then unpause and see if you got it right. All right, so the way I would do this is first, if I know that v of x in general is g of f of x, and that means that the derivative, we're going to use the chain rule, so that's the derivative of the outer function g prime with f of x plugged in, no change, times the derivative of the inside, f prime of x. So that's true at any x, and then we want to evaluate this at x is 1, so we'll plug in 1. That gives me g prime of f of 1 times f prime of 1. So let's start with this. F of 1 is the y-coordinate of the f function at 1. Let's make sure we get the right one. That's the blue function here. Y-coordinate here would be 2, so this is a 2. And that's now what's being plugged into the g prime function times f prime of 1. So now this is at x is 2. What's the slope of the g function? G function is the red function. What's the derivative at 2? So at 2 here we have a corner. And that means that this function is undefined. That does not exist. F prime of 1, though, we could find. That is positive 2 for a slope. But you can't multiply 2 by an undefined function. So we would have to say that this does not exist, DNE. And it says to explain why. So we're going to say because g prime of 2 does not exist due to a corner. Now you can use that language on the AP exam. If you look at their own rubric, they would probably say something even more formal. They would say the slope on the left of 2 is not equal to the slope on the right of 2. That's why we don't have a unique derivative here. So they might even go this far and say the limit as x approaches 2 from the left of a structure that gives you the instantaneous rate of change. That would be f of, or we're equivalent to g of x minus g of 2 over x minus 2 is not equal to the structure for the derivative as we approach from the right. We have x minus g of 2 over x minus 2. I'm only throwing this in because when we looked at some recent AP exams, we saw language like this in their styling. We're not requiring that. It is part of the course, at least at our school. But it's good to start looking at how formal they want solutions written on the AP exam. They might be fine with just stating that this does not exist because there's an abrupt change in the curve or because there's a corner at x is 2. All right, let's look at the next one. This is the last example, I believe. Yeah, last example. Here we want w prime of 1. So we're going to start by saying what is w at any x. That is g of x. There's no reason why we can't plug in x into the g function, take the result, and plug it back into the g function. So we'll use the same procedure. W prime of x is the derivative of the outer function, which is g prime, with g of x plugged in unchanged. Chain rule says times the derivative of the inside function. So there's the generic derivative at any x, and now we can plug 1 in. So this is g prime of g of 1 times g prime of 1. And starting with this g of 1, that's the y-coordinate of the g function at x is 1. That's going to be 1, 2, 3. So that is a 3. And that's now getting plugged into the g prime function, and we also have g prime of 1. So these are slopes of the g function, so the red function. At x is 3, 1, 2, 3. The slope of this function is, let's see, we're going up 1 and over, no, up 2 and over 1, 2, 3. So positive 2/3. And g prime of 1, red function again, would be down 1, 2, 3 over 1, so that is negative 1/3. And so you can leave it like that, or you can multiply these fractions together and get negative 2/9 as the answer. All right. This is definitely one to make sure you do all the homework on it and make sure you can become really quick at seeing this. Whenever you're taking a derivative and the inside is anything other than x, that means you have to do this. Let me just point out one more thing here. Let's say that you have y is cosine of x, and you want to take the derivative. The derivative of cosine is negative sine of x, right? No need for chain rule if what's inside is just the x. But if what's inside is something more complicated, like x squared, sorry, that's y, then the derivative would be the derivative of the outside function, negative sine of x squared, times the derivative of the inside, so times 2x. Okay? And that's true even if what's inside is only a negative of x. That's the simplest modification you can think of. But even just having that means you have to take the chain rule. You have to take the negative sine of negative x, but the derivative of that is negative 1, so that's going to change the sign. Okay, that'll wrap that video up.